So eBPF is one of the hot topic in the cybersecurity world. This is pretty important because it gives you pretty low-level control in the Linux kernel itself. And one of the advantages of this technology is that it is safe, efficient, and it lets you control some kernel hooks at some point in a sandbox environment. And while developing an eBPF program, you're using C technology, but it's a kind of a simple C or minified C. So it is not a full-fledged C or C++ program. So it's a limited version. However, you can create your own sandbox environment modules and do some stuff in order to prevent it. So here I would like to talk about or share in the details what an eBPF program looks like, and what do we mean by hooking some syscalls, and how to interact with those kernel level actions with an application that runs in the user space. So as you can see here, by the way, you can find those examples in this link below. These are pretty simple examples. So one of the first things is that all eBPF programs should have two stages. One, C code or low-level code that runs in the kernel stage, and user space actions that lets you do your own stuff if needed. So in the second item, you will see a map. Maps are a way to communicate, or maps are the communication channels between user space and kernel space, or maybe between two different kernel hooks. So in this simple example, we are using a perf event array type of map, and this is how we catch the kprop CIC calls and sent into the user space. Kprop means that kernel prop. In this presentation, we will hear the kernel prop a lot, and CIC means that actually the shell exec operations that kernel catches. And obviously this is a pretty easy example, but if we go to the next slide. Yeah, right now we have a more advanced and slightly more complicated example. So in this example, what we are using is that the advantage of the eBPF technology, since it's community driven, there are lots of high-level SDKs or bindings that you can interact with your programming languages. For example, our code has been developed in Golang. However, right now the Rust, Go, and also Python are the popular programming language options. And this examples are using Cilium's eBPF bindings, eBPF SDKs to interact with the user space. So it is again simple. In the first stages, we tell that which function we want to hook. Then we bind the objects, because whenever we run this Cilium's eBPF to Go command, the compiled C code also transformed into the Go bindings, and this is how we can literally communicate or control everything in the user space. And finally, we actually catch the events that has been identified in the C program in our previous example, and we can print those events on the user space. So please check out those examples. So how we can use this technology in order to mitigate the problems that Mert explained. So what we came up with is that in all of the cases, there should be an outbound network connection. Even though eBPF lets you communicate or lets you hook other low-level kernel functions, for this example, we want to use the egress traffic, outbound traffic control options. However, we are planning to add more filters, more functions, or more mitigations, and we want to keep this project open source, and we want everyone to contribute it. What we can do is that we can actually query the DNS queries. We can have control over the file system. Maybe we can limit writing or reading in the certain files or certain important resources. We can list the process. We can check if which process are spawned. For example, if an npm install command spawns an shell code or some exa binary, executable binary, we can assume that this is a fish operation, etc. So the options are endless here. But our approach is that whenever an event occurs, we want to capture which process ID are getting outbound, and based on the logic that we have written in the user space, we want to tell the kernel to block or filter those options. However, how to start or how to identify or where to start finding those syscalls? Even if you don't know, or even if you're not familiar with the Linux source code, the easiest way to do that, running the strace command. Strace means that system trace. It is pretty popular command, and you can easily install on any Linux machine. And so, as you can see here, when we run a curl command, we can have some functions written here. So if you want to capture or filter outbound traffic connection, we can use those operations. The first operation is the TCP connect call, and the second best option could be the socket operations. One thing that you should know about kernel programming or the low-level programming is that the execution order is pretty important. So based on the operation that you want to have or you want to provide, some things may work or may not work because of the execution order. However, here in this approach, we are going to first identify which process IDs, PID, process ID, process name, is going to communicate or sends TCP connect request to which outbound resources. Can we go to the next one?